Hey guys, Mr. Betts here. Let's take a look at a couple examples where we can use the second version of the fundamental theorem of calculus to evaluate definite integrals. So the ones I chose are going to be expressions where we can figure out what the antiderivative is pretty easily using what we know about derivatives. So we're just reversing the derivative. So remember, the second fundamental theorem says that we can start with any antiderivative. So we think to ourselves, what do we take the derivative of to get 3x squared? I hope that you recognize that we can take the derivative of x cubed to get 3x squared. Normally with an antiderivative, we would include the constant of integration, but we do not need that here because we can choose any antiderivative, so we're choosing c equals 0. Then we're going to evaluate that from 2 to 5. Remember, we always say from this to this, so we're going from the lower limit to the upper limit. And then we evaluate that antiderivative at those two values, starting with the upper limit. So we're going to plug in the 5 for x, and we get 5 cubed minus 2 cubed. 5 cubed is 125 minus 2 cubed is 8. So we're going to get 117. So if we were to graph the function 3x squared and find the area below 3x squared between 3x squared and the x-axis between x equals 2 and x equals 5, that would be an area of 117. We can do the same thing for sine of theta. This one's going to be a little bit tricky, so I wanted you to think about this one a little bit. So remember, we want to take the antiderivative of sine of theta. What do we take the derivative of to get sine? Well, just a side note here, let's use theta. So the derivative of cosine of theta is the opposite of sine of theta. So if we're reversing this, the antiderivative of the opposite of sine of theta would be cosine of theta. Well, we have positive sine of theta here, which means then that we're going to use the opposite of that. Okay, so the antiderivative of sine of theta is the opposite of cosine of theta. Now, we want to evaluate that from 0 to pi over 4. So we, remember, start with the upper limit. So the upper limit is pi over 4. So we have the opposite of cosine of pi over 4 minus the opposite of cosine of 0. There's nothing wrong with, if you see this coming, if you're subtracting a negative, just put plus there. So plus the cosine of, not theta, but 0. Trig functions, you should be able to evaluate the trig functions at angles like pi over 4, pi over 6, pi over 3, and those angles in other quadrants. If you ever forget them, remember they're based on triangles. So pi over 4 is a 45-degree angle, so we have a 45, 45, 90. So cosine of pi over 4 is 1 over square root of 2. So this is going to be negative 1 over square root of 2 plus cosine of 0 is 1. You could rewrite that as 1 minus 1 over square root of 2. You could rationalize the denominator there if you want. You could combine the fractions by getting a common denominator. None of those things is necessary. If this is free response and that's correct, then box it and you're done. If this were a multiple choice question, I wouldn't be surprised to see this as a fraction with a single denominator, a single fraction. So you should obviously be able to manipulate that algebraically to get that. So I want to point out that we're going to do more of these types of problems. So evaluating definite integrals using antiderivatives, but we're going to hold off on those until later topics when we learn more about taking antiderivatives of different types of functions. The first ones that we're going to learn about are the ones that are kind of like the ones we just saw in these examples, where we're essentially just undoing derivatives that we are familiar with. So again, we'll be looking at more of these definite integral problems as we learn more about antiderivatives.